So, let us continue our discussion on the various pavement design methods that are available in the world, and in fact, I have specifically selected 3 countries: South Africa, Australia and finally United States of America, especially related to the AASHTO ware or the MEPDG, which is quite exhaustive. There is a reason why I picked these 2 design methods, especially South Africa. The manner in which they integrate the pavement construction, pavement management into the pavement design process. So, that kind of an integration is something that ideally at India we should be striving for. Australia comes from a completely different perspective in terms of the rigorous manner in which they handle the axial loads and the rigorous manner in which they give separate distress transfer function for each of the pavement layers. And finally, AASHTO ware which is quite data driven, thousands of long term pavement performance sections, data collected, assimilated, and you can think of it like this is where we should be going in terms of the design strategies. Okay. So, what we will do the South African design method in 2 different videos. Okay. So, this is the South African Pavement Engineering Manual. You should be able to download it, it is freely available, and in fact, there is a full component of Pavement Engineering Manual that is available. I have shown you only the chapter 10 which corresponds to the pavement design. There is a small component of concrete pavement design also is part of it, but that is something that we will not be discussing in this course. We will have a separate course to talk about the concrete pavement design. This is the first sentence that I really liked in the pavement design manual, and it says something like this: pavement design is an engineering discipline somewhere in between science and art, which is very true. Okay. So, in fact, in the last discussion that we had, you must have seen in the distress transfer function how on the left hand side you have number of repetitions to failure for rutting or fatigue cracking, which is the terminal condition, which is related to the initial condition that is given on the right hand side. So, there seems to be some kind of a gut feel, engineer's intuition, uncommon common sense that gets into the whole design part. Okay. And there are few important concepts that you will see only in the South African Pavement Engineering Manual, and that is something that we will discuss as we go along. So, now there is a very clear cut definition about what is called as the structural capacity. What exactly is the structural capacity? The period from an initial sound structural condition to a predefined terminal structural condition. Okay. So, this period is where we are really talking in terms of the structural capacity, because as we discussed in the initial lectures, we talk always as far as pavements are concerned, functional failure, structural failure. Okay. Functional failure is when you are not able to ride your vehicle on top of your pavement with the required comfort level at the design speed, and structural failure is when it completely breaks down. Now, with that context, put this in practice. What is really called as the predefined terminal, or what is called as unacceptable structural condition. You see a road which you think is motorable, but when you are trying to drive on top of it at, let us say, 60 km/h, the geometric design says that you can drive at 60 km/h, but you are not able to drive on top of it. You can call that as an unacceptable condition, in which case its structural capacity, you can think of it in terms of reaching it terminal condition. Okay. The structural design basically here consists of 2 things. One is the traffic demand which comes from the other side, another is the structural capacity. And in fact, in the old ASTO you can actually see ASTO 1993 that was discussed by Dr. Nivita, you would have seen the difference between WTX and WT18. So, given any pavement with a resilient modulus and structural number, what is the capacity for it to take this 80 kilonewton repeats? When the condition goes from, let us say, 4.2 to 1.5 or 2. So, that tells you something about the structural capacity. Now, what is that we need to really match it with? What is the expected traffic demand here? Now comes the most important thing here. This is their schematic of how the stress distribution really happens. So, you can actually see about the half axial tire loads. So, what they really mean as half axle, if this is your single axle dual wheel and you call this as half axle. Okay. So, you see that this is the varying course, there is a base layer, there is a sub base layer, and then this is your existing subgrade, in situ subgrade, and you can actually have two layers on top of the subgrade, what is really called as an improved or imported subgrade. You can take earth from the borrow pits and fill it up here, and base and sub base layer. So, the structural layers are subjected to substantially high shear stresses, the strains are also considerably large, whereas the subgrade is subjected to low shear stress and small strains. The simple idea with which I can express the basic design strategy of South African pavement design method is keep the subgrade away from the impact of high stresses. So, that means push it all the way down, that is the strategy here. So, let us just look into each and every of the design principles one by one. As far as the pavement structural layers is concerned, and in fact, just before I continue, these are the people who also very clearly define what is a foundation for a pavement. See, normally when you are talking about a building structure, building construction, you talk about foundation, basement, superstructure and all those things, and when it comes to pavement, if somebody asks you, okay, where is your superstructure and where is your basement, where is your foundation, you may not really be able to answer. You will say like everything seems to be foundation. No, not really true. So, you can think of the surfacing as something like a superstructure, you can think of the subgrade more like a subgrade or the improved subgrade more like a foundation, and somewhere in between structure to be called something like a basement. Okay. So, they define it in that specific way. So, materials of sufficient strength and stiffness for the pavement structural layers, that is number 1. Number 2 is, so when you say strength and stiffness, you are talking about the modulus properties, material constitution that you are having. Second is, what is the layer thickness? We need to have sufficient layer thickness, and then you are talking about minimum subgrade strength requirement. The interesting part here is, we will be talking about this balanced pavement structure in a short while from now. They would like you to transition from the material with high shear strength and stiffness at the top to the relatively lower strength in a smooth way, and this is really called as a balanced pavement concept. Okay. Now, there are various categories under the design considerations that are given here. We will try to go through each one of this as we go along. So, first and foremost thing, what is the road categories, what is analysis period and design period, what is a life cycle strategy, what is pavement balance, and how do the pavement behave under load. So, in this lecture I will try to discuss with respect to these portions, and in the subsequent lecture we will talk about the pavement behavior under loading. Okay. Right. So, this is their road category they define. Okay. So, you need to think in terms of expressways, national highways, state highways, major district roads, minor district roads, and all those classifications that we have in India. So, similar to that they have the road category, what they call in a very simple way as A, B, C, D. Okay. So, now what exactly is this A, B, C, D? A is a major interurban freeway and major rural road. So, you can think in terms of expressways and national highways. Then B could be something like an interurban collector and rural roads. You can think of it in terms of a state highway, and C is lightly trafficked rural roads and strategic roads. Think of it like what you can say our district roads and rural access road. There are some roads in United States which are called FM roads, what are called farm to market roads. So, that means there is a nearby agricultural field and there is a market somewhere here. So, from the farm to the market. So, these roads provided the required accessibility to take the produce from a farm to the market here. So, they have the requirements are fairly simple. Okay. Now, what is the strategic level of importance that you are looking at? Very important, important, less important, less important. Okay. Now, what is the level of service? We are looking at very high, high, moderate and moderate. And what is the typical pavement characteristics that you are looking at? The reliability that you are looking for A is very high. So, it is 95, reduces to 90, 80 and finally, it just comes to 50 here. And the length of the road exceeding the terminal distress condition at the end of the structural design life is of course 5 here. The design reliability is 95. So, this is 5 and this is 10, this is 20 and this is 50. What do we really talk in terms of equivalent traffic loading? So, if you go by the 80 kilonewton standard axle load per lane, you are looking at roughly 100 million standard axles in 20-year period. So, that is the typical period that they are really looking at. So, this is 10 million, this is less than 3 million and this is less than 1 million during the depending on the design strategy. Now, the interesting thing that you should really notice here is while this period design period is mentioned here, nothing is mentioned here and they only say that what kind of design strategy that you really want to follow. Now, what exactly is the design strategy that they are really looking at? This is the design strategy that they are looking at. Okay. How much is the predefined structural condition and what is the predefined terminal condition. So, that is the whole idea they are looking at, and these are some of the numbers that are given here, you do not need to worry about it. And the daily traffic is, you can think of in terms of what we have in India as CVPD, commercial vehicle per day, and this is given here as EVU, equivalent vehicle units. So, greater than 4000, then 6600 to 10,000, less than 600, less than 500, and terminal riding quality, and this is most important, right. What is the IRI value initial and what is the terminal IRI value? You can see the high quality that they are really looking at here. So, the terminal IRI here is 3.5, whereas you can have that as a starting IRI value for category C vehicle, and the rut level for bituminous pavement is 10 mm, 10 mm, 10 mm, 10 mm, terminal is 20, 20, 20, 20. So, warning sign is 10 mm. So, that means you are expected to start doing your maintenance during this period. Now, for most of you who have been following these lectures, okay, so we are more or less at the last week of our lecture. How can you relate whatever you have learned from IRC 37 to here. Okay. And I want you to really reflect upon it, saying that did we see a separate pavement design classification for expressways, national highways? Did we see a separate classification in terms of IRI, in terms of rut depth for different classes of vehicle? But the most important point that you need to note here is the class of the road may be less important, but the acceptable rut depth remains the same irrespective of the level of service of the road. That is the most important thing. So, to just to give a snapshot of what these highways look like, I have just taken this from the manual. So, this is your category A, what I mentioned as national highways and expressways. This could be category B, this could be state highways, this could be major district road, and this could be village road or farm to market road. So, typically you can think in terms of both these roads, category C as well as category D, and to some extent category B are also, they are undivided 2-lane 2-way roads. Okay. So, that is what it is. This could also be category D, also could be a 1-lane 2-way road. Typically what you see in some of the roads in our rural area, wherein the lane width is something of the order of 5 meters, and so typically one vehicle that is coming here moves to the shoulder, allowing the other vehicle to pass through. Okay. So, now we need to take a recap of the design period and the analysis period, because this kind of definitions, classifications are very important as far as the South African manual is concerned. So, what exactly is a design period? It is the traffic analysis period. If you, in fact, you can just make it as something like this. So, this is where things become tricky. For instance, let us say, how do you do the estimate the likely traffic, and then because you have to do it for how many years, 5 years you want or 10 years, you need to do the projections. For a country like us, where we are we are growing these days, is it a correct way of projecting for 10 years or 15 years from now? Because let us assume the following. Let us say you do your volume count, axial load count, and then use your vehicle damage factor, come out with 30 million standard axles, and then let us say you design it for 10 years. And whenever a new facility is constructed, there is always a tendency for the traffic to move in that direction. And what if this whatever is the design period that you used, this whole 30 million standard axles or 40 million standard axles comes in the first 4 years, and this is not something that you really expected. So, which means what you have designed for 10 years, you are going to have a problem at the end of 3rd or the 4th year. Okay. So, it is always not a great strategy to look out for projections for a country like India, in which highways are being laid, being maintained, there is a spurt in the truck traffic growth when this is happening, to project for too long a period. Okay. So, we might end up with some kind of a failure. So, what we really need to do is need to kind of look at 5-year period, and in fact that if you are familiar with IRC 37, 2012 there used to be charts even for 250 million standard axles. Luckily now we have only up to 50 million standard axles, which makes actually a lot of sense. So, what exactly is the design period? It is your traffic analysis period. Now, the analysis period, okay, that time that any design strategy must cover. For instance, to give an example, the geometric design life. Let us talk about a simple thing. I think all of you must have taken a course on geometric design. So, there will be design speed, posted speed, and so on and so forth. So, let us say you have constructed a highway and carried out the geometric design for, let us say, 80 km/h speed. So, that means your radius, your super elevation, everything has been taken care as far as this 80 kilometers speed is concerned. Now you have high speed trucks, in fact many of the trucks that we have in our country are very good, they can go up to a much higher speed. Now what will you need to do now is to make corrections in the highway. Is it really possible? It may not really be possible, because you have designed something for 80 kilometer per hour. Now if you want to elevate it to 120 kilometer per hour, you need to make major corrections in the geometry of the highway. So what I am trying to say here is, the analysis period is the time that any design strategy must cover. So that means if you say this road is going to be an 80 kilometer per hour road, if it becomes a 100 kilometer per hour road, let us say at the end of 5 years or 10 years, okay, you want to really call that as an analysis period. And then performance period is where any pavement structure will last before it needs a rehabilitation. So design period, analysis period and performance period. So let us not forget all these things. Okay. As far as the South African manual is concerned, for category A roads it is 25 years, for B roads it is 20 years and for C roads it is 10 years, and for category D roads they do not really say too much about how much should be the design period and analysis period, they talk always in terms of the reliability. So we will leave it like that. Yet another important thing as far as the South African manual is concerned is, when you do the pavement design itself, you kind of link the design and the maintenance. That is something that we do not explicitly take into account in our pavement design process. See, for instance, you see on this y axis riding quality in terms of pavement serviceability index is given. So this is your constructed riding quality, and I am talking in terms of two cases here, what is really called as the reduced initial construction cost. And in fact, it always makes sense to do the construction for an initial period of 5 years or maybe 10 years, and then if depending on the traffic growth, axle load growth, you can actually keep increasing the structural capacity of the material. And that is why, I must have said this before, pavement life of a pavement and all those words that people use do not actually make any sense, because you can keep increasing, extending the life of the pavement by keep doing a rehabilitation strategies, right. So this is the whole thing. So now take a look at it. The structural design period is, so let us say 10 years or 20 years, and this is your analysis period 20 to 30 years. So you are talking in terms of the PSI reducing, and then you get a trigger, small resurfacing you do, then the quality increases, and when it comes to this particular part, this is your terminal riding quality. So what could be your terminal riding quality? In fact, if you talk in terms of 20 mm, 10 mm, so let us do the following. You will write somewhere here that this is 10 mm and this is 20 mm. So you need to do a major structural rehabilitation, and then it goes on like this. So this is your initial reduced initial construction cost. Now what you are talking about is reduced future construction cost, because this is always a problem. Whether whatever money you spend 1 rupee now, the same 1 rupee has a completely different value 5 years down the line. So do you want to reduce the initial cost, or do you want to reduce the future construction cost? Now this is something that we do as part of the pavement infrastructure management course, but what is interesting in the South African manual is these things are integrated part of the design strategy. So you can actually take a look at the constructed riding quality, no maintenance all the way here. So there is no big difference between the design period and the analysis period. You all the way keep just doing only a resurfacing here, which is actually cheaper, and so that is why you say that the future construction cost is reduced. So, when you now do your design, you also need to tell the pavement owner that I am going to do a design. So, the initial construction cost is going to be high, but whereas the future construction cost is going to be less, and that part has to be integrated during the design period. Now comes the next concept, which in my opinion is a very important concept, is what is called as a well balanced pavement. What is a well balanced pavement? So, the material quality gradually and smoothly increases from the in situ subgrade to the structural layer and surfacing. So, that means you do not give a drastic jump in the modulus value as you go from the subgrade all the way up to the surface of the material. So, this is what is really called as a well balanced pavement. Now, if you do not do that, what can really happen is the South Africans introduced a very interesting concept called traffic molding. So, what exactly is this traffic molding? If let us say one or two of the layers are stiffer, these layers will initially carry most of the loading, and but they will deteriorate faster to achieve balance with the rest of the pavement structure, and due to this particular process there is something called the traffic molding that happens. So, you can use actually a dynamic cone penetrometer to get the test. So, let me explain this using this cross section. Okay. So, let us take a look at this one. So, let us draw how the modulus is varying. So, if you assume that the modulus varies in this way gradually, if it is varying. So, this is the modulus, and so let me draw some of these lines here. So, there is a gradual variation that you see, you will call it as a balanced pavement design. Now, instead, so let us do something else. So, let us say we do something like this. What can happen? This is a stiffer layer and there is a drastic discrete jump here, then there is another jump here. So, most of the layers that you see here can actually take more stresses than what it has to, and because of this there will be a deterioration. So, after some point of time what you will see is, you will see that it has become something like this. So, this is called traffic molding, and in fact I would like you to also recollect the discussions that we had in the initial lectures, wherein we said that if you provide a bituminous layer or any of the binder or the surface courses with a considerably large modulus value, what can happen? You might reduce the vertical stress, you might reduce the deflection, but the shear stresses can actually increase, the tensile strains can actually increase. So, that is not really a great way of doing it, and in fact what you could do as part of your design project, which anyway I am going to talk later, is to verify whether any of the IRC pavement sections are well balanced. Okay. So, and how do you really make it well balanced, and that will be really interesting to do at the graduate level. So, if you are an MTech student who is taking this course, and if you would like to do your project on pavement design, then you may want to think about how do I verify whether any of the cross sections that are given as part of the IRC 37 CATLA is well balanced, or how do I design a well balanced pavement. So, that is the first thing, right. Then you can also try and see, but of course it will take some more simulations, you need to do some finite element analysis. So, we will not go there, but it will be interesting to see how exactly this traffic molding really happens, because this is something to relate with the strains to the damage loss. Okay. So, that we want to do it. Then there is also a concept of a shallow foundation, like what you have for the foundations, they also define in terms of what is a shallow pavement and what is a deep pavement. So, if you are going to have the pavement strength of the pavement is distributed in the upper layer, it is called as a shallow, and if it is distributed throughout the depth, it is called a deep pavement. Again, as part of an exercise, you may want to also relate a balanced pavement with the shallow pavement as well as with the deep pavement. The interesting part is related to the inverted pavement. Now, what exactly is this inverted pavement? In an inverted pavement, you can have a base layer which is a high quality granular layer, but your subbase could be a cement stabilized layer. So, let us take a look at it. So, let us draw. So, this is your varying cores, this is your binder cores, this is your base cores, this is your subgrade, subbase, and this is some capping layer, and this is your subgrade. Varying cores, binder cores, base cores, subbase cores, etc. Now, what will happen? And of course, we will write E1, E2, E3, E4, E5, E6. Now, let us take a look at these two, E3 and E4. Now, E3 can be greater than or equal to E4, or E3 can be less than or equal to E4. So, if you are going to have some kind of a layer in which this is like this, you are going to talk in terms of a layer which is an inverted pavement. You can, in fact, you can even remove all these things and provide one thin asphalt layer. But what can really happen is an inverted pavement is not really a balanced pavement initially, but what will really happen is it can shake down and become a balanced pavement later. So, what does that mean? So, that means this, and in fact, this is something that you should try to do using a Kenpave kind of an analysis, try to put across modulus values that are slightly more than for the higher layers and see what happens. And again, this is something that you could do it as a small project. So, now what can really happen is, since this has more modulus value, it can take more load, and it can also deteriorate faster. So, slowly the E3 value, E4 value will remain the same, the E3 value keeps let me just rub it, okay. So, let me write it carefully. E4 is higher, E3 is lower. So, this can keep coming down and it can reach the value of E3, in which case you will get a balanced pavement. That is the whole idea, and I have used a very interesting word called shake down. It shakes down to one optimal status, what is really called as a resilient status. Okay. So, now we come to the another important concept. Again, this is very interesting because these things are mentioned in the pavement design process itself. So, now you have designed a pavement, and I want to ask you this question. So, you say that you have designed a pavement, what is the maximum deflection that you are likely to get, okay. Because most of the time what happens is in the way in which we do the design is, so you have traffic, you compute the vehicle damage factor, you find out 5 years or 10 years what is the million standard axles, and then you have the material properties, and then you have distress equations, and then you relate it, and then you say that okay, I want 50 million standard axles and this cross section can take 60 million standard axles, I am fine. But what I really want to do is what is the deformation that you will get for this. So, I want to know that number. So, you are going to see that they basically give you a prescription that if the deformation is of the order of 500 microstrain, a pavement under good condition, this is the maximum deflection. So, this will be an interesting point for us to even study, like what is the deformation that you are seeing here, and it is also very interesting. So, when I take the load, and this is an analysis that you should be able to do it in KenPave. So, what you do, you take a pavement and you have many cross sections there, apply the maximum load, you do not need to worry only about 560 kilopascal. What happens if there is an overloading? Apply 1000 kilopascal, apply 2000 kilopascal. Use your KenPave analysis and go on all the sites, try to see when the deformations will become 0 and if it is going to extend beyond 2 meters, okay, then you are basically not looking at a great design. So, this is your design that you need to be really worry about. So, how do we really find out how the pavement will behave during working conditions? Either we can do a simulation, or on a pavement that is immediately constructed, we could try to find out using a what is called as a falling weight deflectometer. So, I am sure you all must have heard about this word falling weight deflectometer. Basically, what we want to find out is what is the extent of the deflection bowl, and from the deflection bowl how do we really read what is the extent of the deflection. So, we will discuss everything in the next lecture.